you so much. Let me first start by thanking you, Athena, everybody else who's done the organization and for accommodating us virtually. This has been quite fantastic. Very excited to talk to you a little bit about some new work. First, let me say that I'm not going to give this talk that some people might be expecting, but I do want to highlight that if you want to see some things about my multi-scale predictive representations, look at the review in 2020, and please go and see Eva Brunek's brilliant work that I was very fortunate to work with her, and we recently published in JNeuro. This is the two set of studies that I've highlighted in the top that I'm going to talk to you about. And the ones that you see below are also very highly relevant. I will not talk to you about them, but I would like to highlight first the Arthur Giuliani work. We have just released the beta version for this workshop, so you guys can take a look at it, called a benchmark NeuroNav, or a benchmark for neuroscience-inspired learning, and Arthur Giuliani, that some of you might know. And I chose a number of neurally based navigation works that are pertinent to modeling, and you can go and play around with different RL models and different environments and benchmarks. Okay, what makes navigation human-like? And can we explain what makes navigation human-like using video games and reinforcement learning? I think that games are a very good place to test this, because about 3 billion humans worldwide play games, which during the pandemic was a saving grace for a lot of us. And since we have a sort of opinion request here, I'll just start by saying that I don't think passing task benchmarks is enough to make AI human-like. Why? Because, you know, crossing a human limit or doing superhuman work does not mean that you did a task human-like. Moreover, we have some colleagues, Siddhartha Sen, that has been working on showing that chess masters, when they look at the results of AI that beats chess masters, and they look at the trajectories, it doesn't appear to them like the trajectory a human would produce. So it's correct that AI can exceed a score that humans have, but that doesn't mean that it behaved human-like, or that its mechanisms were human-like to generate that behavior. Second, behaving like humans on some tasks is also not enough. For instance, some might be passing some Turing test or other, produce something that is human-like or other, but it might not necessarily have brain-like mechanism, nor might it generalize for other kinds of very related tasks. It might not transfer. Finally, having some kind of partial architecture that's similar is not enough. For instance, as we know, the very famous CNNs, convolutional neural networks, are not robust to adversarial attacks or even adversarial patches. As you can see, if there is a banana and you just add a little patch next to it, all of a sudden this would be recognized as a toaster. There have been some fixes to this, of course. Some folks did it by adding a retina, etc. But there has been so far no test that actually looks at both human-like errors on, because we also are susceptible to some of these adversarial attacks, and accuracies on this. So that's still an open question. This is how I wanted to highlight why I think it's important to have these sorts of Turing tests and architectural tests. So both neurally plausible, neuroscience plausible benchmarks, and also navigation Turing test in this case, or other kinds of Turing tests, which simply stands for ask humans, does this behavior look human-like to you? So in order to ask this, we started with something that was purchased from a company with the coolest name possible. Ninja Theory was bought by Microsoft and hence Xbox in 2020. And they had the 8x8 multiplayer game that is very cyberpunk and interesting, but it has very interesting navigation. So we stripped that game to make it simple for this first part of our work. And we turned it into a single player navigation just to test a number of things. I'll show you what we have done here, and I'll tell you a little bit about the moonshot of what we hope to do in the future. Okay, so the first part. So I'm going to play these videos. First, I'm playing the video on the left, and look at this behavior and let me know which of the two, the left or the right one, you think is more likely to be played by a human. So you're currently watching the video on the left. Hopefully you can see it. This requires our audience participation. So let me know after this is finished. I'll play the video on the right. Let me know which one looks more like human, as in a human is playing as opposed to an AI. All right, now I'm playing the video on the right. I hope you remember the video on the left. So I see that 2 people in the chat have responded. What do the people in the room think? I think I can still hear you. Left or right is human? Left is. So in this case, the left video was human in this case. And the interesting thing is that depending on your expertise, some people who are not an expert, they think that the right one is human. All right, I'll show you another set of videos. So now let's take a look at another set of videos. So this is the video on the left. I think it's enough. And this is the video on the right. So the question is the left video or the right video human? Right. Okay, so in this case, both of them were AIs, but you are correct. Just as a lot of our judges, that the agent on the right behaves more human-like in a very obvious way to you guys. So this is how we did exactly how we did this test. So sometimes, so a human judge would sit in front of 2 videos, and once the video, one of the videos was human, and the other time there were 2 agents that were being compared. And the kinds of agents that we sort of tried out were state-of-the-art-ish agents, because we had to simplify the agent architecture sometimes. One was a symbolic agent that had low dimensional representation of the goal and the game states and had simple feed-forward networks. Another one was a hybrid agent with symbolic observations, like above, like the symbolic agent, but also 32 by 32 depth buffer, a fully connected neural network, a CNN, and the action space for all of these cases was either doing nothing or going forward and left or right. And the state-of-the-art algorithms were inspired by this paper that had been published before we started our work. Oh, glitch. Okay, let me go back. Do you guys see the glitch? Yeah. All right, okay. So this is the way that people were tested. They were shown the 2 videos. They would ask what they thought after choosing, and then they were asked how certain they are. In the study, we had, first we started to test this on Microsoft employees internally. And so there were 6 trials where participants saw a human versus hybrid agent. Unbeknownst to them, 4 trials were sprinkled in where there was hybrid versus symbolic agent. In the second study, we had human versus symbolic and sprinkled 4 trials of the 2 agents versus each other. As you can see in study 1, where the hybrid agent was the one compared to humans, it's very clear. The blue corresponds to, hybrid agent, and the orange to symbolic. And on the y-axis, you can see how many out of the 4 judged the one or the other as more human-like. Interestingly, the pattern is still significant towards hybrid in study 2, but maybe due to familiarity, they would confuse more symbolic in study 2. If you looked at these results, then you would see that, and this is from our ICML 2021 paper, you would see that none of these 2 agents actually passed the Turing test compared to humans, but it seems like they're confused some more than others. And their certainty is kind of all over the place. They're not very certain about what they're judging either. So just a kind of interim summary, none of them passed the Turing test. We replicated these with MTurk participants, and we added another one which did imitation learning with reward shaping. As you can see, the difference between Microsoft employees and MTurk participants was that some MTurk participants reversed the situation, meaning they were always correct, but in the wrong way. So they were always confusing human and AI with each other 100%, which is kind of surprising. But importantly, we saw that the imitation learning with reward shaping actually had a lower mean, closer to passing the Turing test, because as you can see, it's very sort of all over the place still. So in short, none of our state-of-the-art or even imitation learning with a lot of reward shaping completely passes the Turing test. When we analyze what people said, some people said some answers like this, for instance. The character in video B runs in straight lines and goes to where it needs to go. The character in video A is running in circles into objects, etc. And so we started to, well, not we, very, very talented colleague of ours, Evelyn Zuniga, who did all of this kind of with a heroic amount of work. We did a coding of these, for instance, that smooth physical movement and goal directed are human codes, and AI codes is object hit and goal indirect, etc. And when you compare the kind of keywords that were used, or the annotation from the annotation process, you can figure out that human likeness was associated, for instance, with goal directedness, particular physical movement, not running into object, not walking into flowers and gardens. All right, I told you about this. Let me take a look at time. Okay. I want to tell you a little bit more about the architecture and the game. This was the map of the game. There was these sort of spots here where they had to jump through these launching pads and then start to move around in these areas. And then there were different goal locations. And the symbolic agent, as I mentioned earlier, it receives symbolic inputs, which are very simplified and diminished, like angle, distance, etc., and then has a bunch of forward layers. The hybrid agent has that, but also has sort of information about the visual field, and it receives some copying and a particular resizing, and then passes through convolutions and then feed forward. So it's a little bit more visually oriented as well as symbolic. And just to compare agent results on the game, the behavior of the agents, if we were only looking at the two agents alone, is very comparable, as you can see here. On the left, you can see how long it took to get to the goal, and on the right, you can see mean episode rewards, like the amount of rewards they got and how long it would get to train is comparable, although hybrid is slightly better. So as you can see, all the differences of them that we saw was based on how humans interpret their behaviors. All right, just to make sure that we get to a lot, I'm just going to tell you about another thing that we did, which was we did an automated NTT, or a navigation Turing test, which is instead of a human judging whether something is human or human-like or not, we started to train artificial judges so that we could potentially automate this process of navigation Turing test. Turns out it's not as easy as you think. So what type of input did we give our artificial judges? So some artificial judges were only given symbolic information. Some artificial judges were given the top-down trajectory of how the agent had moved around. Some artificial judges received just visual input, and some artificial judges received a barcode image. And but barcode images, you collapse a lot of images, mean of all the images as one row, and you collapse all the rows on top of each other. It's a first-person perspective of this kind of agent that's running around. So as you can see, there is some zigzag here and shows how many turns the agent took. All right, and then we tried 6 different artificial judges, or ANTT, for the artificial navigation Turing test, or automated navigation Turing test judges. As you can see here, we had 3 categories for each of them too. So the symbolic models included symbolic feed forward and a GRU, or GRU. They were inspired by the discriminator architectures in adversarial imitation learning. And then we had a visual feed forward and GRU, and they were sort of also comparable to the discriminator part of adversarial imitation learning, but with the visual observation part. Then we had a top-down on the barcode, which had CNNs and UDGs. Now let's take a look at the results. So first of all, oh, I just said this. Oh, one thing about the top-down sort of trajectories, as you can see, it's not super easy to tell the difference. Here, I want to ask you, just for audience participation, which of the left or right barcode image do you think was created by a human, or is based on the navigation of a human?
Right.
The left one, actually. It turns out humans don't like zigzagging that much, possibly because we get dizzy. And so it was interesting that that's why you can see that this is actually a useful thing for one of the judges to have. All right, long story short, let's take a look at human versus agent accuracy. Pretty much all of them, other than just the simple CNNs and the feed forward visual work, anything that's a little more complicated than just the CNN or feed forward can actually dissociate between human and agent nicely. However, if you look at how it's ranking human agents, like human versus the 2 agents, the ranking is messed up. As you will see a little bit more closely here on the right side, in fact, none of them is good at figuring out which of the 2 agents is more human-like, something that you guys were actually very good at, and you had some level of certainty, so did our participants. So it turns out that they are even worse at ranking, very bad at ranking, in fact, when it comes to ranking of the artificial agents versus each other. So what does it tell us? It tells us that although it was easy to discriminate human versus agent, maybe it wasn't for the right reasons, or maybe the agent, the artificial judge, didn't learn the right reasons because it couldn't generalize it to comparing two agents and figuring out what human likeness is. So both of these, I put forward a lot of work. We have published 2 papers, but all of this just to say how difficult it is to actually capture, first, human-like behavior, and second, even judge human-like behavior artificially. Something that we hope to do in the future, this is a shot, spoiler alert, this is a shot if you haven't seen, maybe I shouldn't say, where 2 artificial agents that are the same thing are sort of facing each other and having a conversation. So maybe we can have this ANTT, or artificial neural net navigation Turing test, as a kind of a metacognitive signal that's working in the background and informing the agent how to update its behavior. But as you can see, we need to improve both architectures that generate the behavior and architectures that judge the behavior. And maybe this is how we sometimes adjust our behaviors in social settings and learn how to behave in the world, which is a part of us is generating and a part of us is comparing, is this human-like or am I acting like an alien? And then updating our behaviors. Okay, so state-of-the-art agents didn't completely pass the Turing test. And hybrid was better than symbolic, not surprising. And at the same time, maybe in the future, we can have inbuilt artificial judges as meta-learning sort of parts of the architecture that can improve this. So to come back to the opinion piece, passing just benchmarks is not enough. Just showing some behavior, human-like behavior in some tasks is not enough. And having some human-like mechanism is not enough. In order to generalize beyond samples and have true human-like AI, we might need to integrate all of this. Thank you so much, and I hope I have left some time for questions.